Welcome back. This is the second part of the lecture on how quantum tunneling is relevant to alpha decay. So, before we move on, let us just recap certain important um, concepts that has been covered in two previous lectures. So, the first thing is that there is an activation barrier for alpha decay. How was this found? This was found via certain experiments. For example, this is a nucleus that spontaneously gives out an alpha particle with this energy. If this is the case, what would have been a reasonable expectation is if you have a projectile, let's say the projectile is an alpha particle of sufficiently high energy, this alpha particle projectile has this energy much more than this alpha particle that is emitted out of this nucleus. If this projectile is thrown at uranium, the alpha decay does not occur. Okay. So that was sort of puzzling. So just another piece of information is how did we get this projectile? This projectile was obtained from this nucleus. This is alpha emitter. This emits alpha particle of this energy. Despite uh, uh, the impingement of this alpha particle onto this nucleus, alpha particle decay did not occur. So it was later understood that this is because of a Coulomb barrier, because as this alpha particle gets closer to this nucleus, both are positively charged. Therefore, there is an electrostatic repulsion, right? This 2 indicates the charge on this alpha particle. Z indicates the number of protons in this nucleus. This indicates the electrostatic repulsion. So later, it was also found that the Coulomb barrier is quite high. It was about 22 MeV, so which is much more than these numbers. If you have an activation barrier of this magnitude, you would have thought that the rates alpha decay will be quite less, but that was not the case, and uh, there was the apparent enhancement rate, despite having a large Coulomb barrier, is because of quantum tunneling. This is what we covered in, I think, two previous lectures. We have covered these kinds of issues. In the last lecture, we introduced quantum tunneling. What is the connection between this lecture and this lecture? So in this lecture, we said that there is an activation barrier of 22. Okay. So that is like this activation barrier that was introduced in the previous lecture. Okay. So your system does not require 22 electron volts to cross this activation barrier. Even if your system has lesser energy than 22 electron volts, you may see some finite rates. That is what we are going to be utilizing to explain the rates observed in alpha decay. So this aspect is what is referred to as quantum tunneling. That is, even if your energy is less than the potential energy, unlike in classical mechanics, in quantum mechanics, you may still cross this activation barrier and get through the barrier to this region. So in the previous lecture, we had stopped somewhere here. So this theory of alpha decay was developed by a very famous theoretical physicist called George Gamow. He has also written very interesting popular science books. So you should also take a look at them to understand many aspects of quantum mechanics and relativity and so on. So in Gamow theory, the alpha particle is preformed in the nucleus prior to emission. Okay, so there is no activation barrier for the formation of alpha particle within the nucleus. Okay, so that is not the main reason for activation barrier. It is the competition between Coulomb energy, Coulomb electrostatic repulsion, and the strong nuclear force, right? So that is the reason for activation barrier. Uh, so whenever there is a minima or a maxima, it is always because of a competition between two contrasting behavior. Okay, so the two contrasting behavior are the following. The first behavior is the Coulomb repulsion. Okay, so if you think about Coulomb repulsion, when you have an alpha particle, as the alpha particle gets closer and closer to the nucleus, the Coulomb repulsion will be greater. So you can, instead of imagining the alpha particle getting close, you can also think about emission of alpha particle, right? So if the alpha particle is emitted, the repulsion between the nucleus and the alpha particle is in this following manner. So, and this strong attractive behavior is because of strong nuclear force, right? So in this lecture, we had mentioned that when the Coulomb barrier peaks, okay, um, after some distance, the strong nuclear force kicks in, right? So that is what we are showing here. Okay, so till some distance, there is the strong nuclear force is not felt by the alpha particle, but beyond this distance, the alpha particle feels the strong nuclear force. So there is a deep attractive interaction. So there is a deep well, but when the alpha particle is beyond certain distance, the strong nuclear force is not felt. The only force that is being felt of some value, of some significant magnitude, is the Coulomb repulsion. Of course, there is gravitational interaction and so on, but that's too small to matter here. So, okay, so the barrier exists. A barrier exists because of the competition between Coulomb repulsion and the strong attractive forces. All right. So, okay. So we are not going to solve these problems exactly using quantum mechanics, but we are just going to use this results of the analysis. So here, P indicates probability of the alpha particle getting through this barrier. So what is T? T, you can think this as the kinetic energy of the alpha particle, right? So we had earlier mentioned that some values, we gave some values, right? So for example, in this lecture, we had given this as the value. Okay, so if the alpha particle comes out with 4.5, that is indicated in the schematic by this value. Okay, so this is the kinetic energy available to the alpha particle. It comes out with let's say with that kinetic energy, and this kinetic energy is less than the activation barrier. But despite this energy being less than this energy, the alpha particle is able to tunnel through because of its quantum mechanical nature. And the probability of it tunneling through is given by this formula. So this is derived in, for example, in this book, as well as in standard textbooks on quantum chemistry and quantum mechanics, which will give you the probability of tunneling. So let's just look at what are the quantities that go into the formula. So here, UR is the this UR, this is the activation barrier. T is the kinetic energy. So this is a negative sign here. If the difference between this and this is large, the probability is lesser, okay, because of the negative sign. And there is another quantity, mu. Mu is the reduced mass. This is the mass of the alpha particle. This is the mass of the daughter nucleus that is left behind after alpha decay. This as a unit of mass. Okay, this is called reduced mass. This is introduced, probably you might have seen this in some classical mechanics or general physics class. If the reduced mass is greater the probability is lesser, right? So when, let's say, if you have um, uh, H and deuterium, okay, so between H, that these are all isotopes of hydrogen, right? If you have H, which has only one proton and no neutron, and deuterium has one proton and one neutron, the deuterium atomic mass is more than the atomic mass of proton, let's say. Therefore, the atomic with the change in atomic mass, the reduced mass will also change. And the greater the reduced mass, the probability of tunneling is lesser. So two things, the difference between this and this, if it is large, the probability will be less. If the reduced mass is large, the probability of tunneling will be less. Next is, how do we think about the rate? The rate will depend upon attempt frequency, the number of times the particle tries to cross the barrier, times probability of crossing the barrier. So we need to find the frequency, attempt frequency. How do we get it? You can get it by, let's say, if we know the velocity of the particle here, and if the velocity is known, that you may know from, let's say, kinetic energy. If the velocity is known, the time taken for the particle to cover this distance, right? So this is R1. So as it goes here and comes back, it covers a distance 2R, 2R1, right? And that is the distance it has to travel divided by the velocity will give you the time it takes to travel this distance. The inverse of that is the frequency. So nu by 2r1 is based on the velocity of the particle and the distance it travels to come back, right? So you can imagine this particle to be oscillating, and the frequency of oscillation is the attempt frequency for crossing the barrier. So how do we get nu? Okay, or V, okay? So this is obtained from what is called the de Broglie wavelength, okay? So the formula for de Broglie wavelength is h Planck's constant divided by momentum. So this is the reduced mass times velocity is the momentum. So R1 is assumed to be the de Broglie wavelength of the particle, okay? So if I know, again, there's another quantum mechanical concept that you have to seen in your quantum chemistry class or quantum mechanics class, or just look at the Wikipedia link for de Broglie wavelength. So lambda de Broglie wavelength is equal to Planck's constant divided by momentum, right? So once you have the kinetic energy, you have the velocity. So how do we get R1? We have already looked at the structure of the nucleus. There are scattering experiments. There are ways to get R1. So I know R1. So what is the assumption Gamow made? Gamow made that this is of the order of de Broglie wavelength. Once you have that, I know velocity. Once I know the velocity, I know the frequency. So what is the decay probability? Decay probability lambda. This is not the de Broglie wavelength. Okay, it's unfortunate symbol. So this is the usual symbol for de Broglie wavelength, but here this lambda indicates the decay probability. Okay, alpha decay probability. Alpha decay probability is equal to probability due to one attempt times the number of attempts. This frequency is the attempt frequency. So these two quantities gives you the decay probability, right? So this P is the same as this quantity. This F is the same as this quantity. We're not going to solve this. So with all these things, we can get an expression for decay probability. So this can also be simplified, okay, further, okay, using these formula. So what are the things that go into this? This is, there is this Coulomb repulsion, okay, also gets into this formula. So this 2 is a charge on the alpha particle, Z is the charge on the nucleus, and so on, okay? So this is the kind of theory that is utilized for explaining alpha decay. So if you want to understand in some detail, you have to go through quantum mechanics of finite barrier, crossing a finite barrier, and then pretty much that level of quantum mechanics is good enough to explain alpha decay in some detail. But hope we have given some flavor on the quantum tunneling theory for alpha decay in this lecture. So these are the predictions of um, from gamma theory. So these are the typical alpha emitters. This is the kinetic energy, because that is also has to be known. R1 is this distance. T is this quantity. With all these things, you can get a value for decay probability. The calculated decay probability compares reasonably well with what is measured experimentally. Okay. So just imagine this is a very complicated problem, right? Because the formula for strong interactions is not known. Therefore, we just use some model potential to represent this interaction. Um, there are many unknowns, but despite it being a very complex problem, a rather simple theory was developed, and the predictions of the theory compare reasonably well with experiments. Okay. Um, the agreement is in general good. When does it fail, or when is the comparison not that great? There are larger deviation when we consider odd nucleus, odd even nucleus, even odd nucleus. We have looked at these symbols. This means there are odd number of protons or odd number of neutrons. Um, these kinds of symbols were introduced some previous lectures, and for some specific neutrons, right? So typically, where does it fail? Okay, you would anticipate based on the previous lectures. We'll mention the reason here also. So this approximation of alpha particle preform more readily is most correct in an even nuclei. Okay. That is, if you have even number of neutrons and even number of protons, this approximation is very well, um, is mostly true. So in this case, alpha decay theory of gamma is more well obeyed, and it fails for magic numbered nuclei, right? You would have anticipated. Okay, whenever we have magic numbers, there are drastic difference in stability, and typically we have to introduce some aspects of detailed aspects of shell theory to explain these features of nucleus. With that, we have completed our discussion on alpha decay. In the next lecture, we will move on to beta decay. Okay, beta decay is the most common radioactive decay, but the first set of experiments on radioactive decay was typically illustrated via alpha decay. Okay, because one of the reasons was that supposing you are trying to initiate radioactive decay by throwing a projectile, the projectile you would be using is alpha particle because the energy and momentum transfer is much better with an alpha particle because it has a reasonable mass and charge. Therefore, it can be accelerated. Let's say you have high kinetic energy, and because of its high kinetic energy and mass, the energy transfer and momentum transfer between alpha particle and the nucleus is much better than other kinds of interaction. So alpha decay was have been studied a lot in earlier um, years of radioactive decay, but the most common radioactive decay is beta decay, which will be introduced in the next lecture. Thank you.